Hi everybody, I'm Aashish Panta. I'm a graduate student at the University of Utah here, and today I'm presenting some of our work that we have been doing with large-scale data sets. Uh, we have like a lot of collaborators working on this project. Few are mentioned here, but there are a lot more. So today, like scientists are generating tons and tons of data every day in peta-scales, maybe from multi-climate models or satellites or all the simulations. And it is very important to analyze this data properly because they help us understand the long-term environmental trend, predict climate changes, and so on. But with these large data sets, there are like a lot of challenges in terms of processing them. For example, storing these petabytes or peta-scale of data sets on a cloud or server is very costly. The second one is the traditional tools that we have do not offer the flexibility to interactively analyze these data sets. Uh, so as a user, you would usually need like thousands or like very high amount of CPU or GPU processing power to analyze these large-scale data sets. And even if you have the storage or the computational resources, if you store the data on the cloud or server, it is very hard to transfer the data to your local machine every time you want to run some analysis. So this insufficient bandwidth will be a major bottleneck for analysis of large-scale data sets. So in order to solve this, we actually developed this architecture on like 3 steps. On the first one, we developed this web-based architecture where you can access the web-based dashboard from anywhere with an internet connection. We deploy these customizable widgets that you can add to any dashboard from our framework. The second one is we implemented a data fabric abstraction layer that simplifies the query that you make to ask for like data sets. So for example, if you want like a certain region of the data set, then you don't have to know where the data is located or how the data is hosted and so on. We also optimize the data streaming from cloud server. So we basically took the traditional row measure data format, regraded it such that we use like space filling curves to make this tree-like structure where at the very top level you have this very coarse data set, and as you go down the tree, you keep on getting more and more refined data. So this data layout, we call this open pieces, where you have this very 2x2 data or 3D data set, and you basically reorder how the data is encoded. The second one is we support various lossy and lossless compression algorithms. For example, here you can see that we took like 25 terabytes of climate data from NASA supercomputer, and we tried to do lossy compression and lossless compression as well. And we were able to get almost 6 times compression factor with a very negligible mean square error. And we also support both caching at like server level and browser level. That helps us optimize the network utilization as well. So our data fabric abstraction layer allows the users to query like region of interest, the spatial resolution they want, the numerical precision they want, and the maximum data size that they can handle. And our abstraction layer will know where to get the data from, which data format to query. Maybe the data is in netcdf format or sdf format or TIFF or anything. And we also support like compression, so we know how to reduce the data at the very source. So why is this important? It is because it helps, so it actually removes the complexity, so users do not have to understand what is happening beneath all these. It is very convenient, and the data transfer is faster as well. So any data that can be loaded as an array into memory can be converted into our format. So first of all, we create a basic IDX file with the metadata, like fields that you are interested in, dimensions, timestamps, and so on. And we open the netcdf file or TIFF file or any data format that you have, and we read them as a NumPy array. And we use open pieces functions where we write the data, we encode the data in memory, and then we write it based on this like hierarchical format that we just said. And we can apply the compression and upload it to cloud as needed. So that's how the IDX dataset is created. Now once the data is there, you can first load the metadata using a very simple Python function and pass like combination of parameters like timestamp, quality, resolution, bounding box, region of interest, or anything that you want. So based on all this framework, we developed these interactive and scalable visualization tools. So for example, the one that you see on the top right, there is a NASA Demon dataset. We made almost 1.1 petabyte of climate data available from the browser. If you want to, you can scan the QR code and have access to these petabytes of data from your phone as well. We provide a bunch of interactive facilities, interactive features like play over time, change the variable, model. If you want to know the stats of the data set, you can do that from the browser as well. If we have some time, we can do a demo as well. But yeah, and we have all these amazing features on like peta-scale datasets from the browser itself. So some of you might be familiar with the CMIP6 dataset as well. So it's almost 37 terabytes of climate dataset that was originally stored in netcdf files. But we encoded this with our IDX format and made the dataset publicly available from web-based, using like web-based architecture. So although the data is like 37 terabytes, you can actually access all of these from your phone with just an internet connection. And for cases if the internet is slow, we provide that resolution slider up there that lets you query like less amount of data with like more coarser visualization. And so this is something we developed in collaboration with the climate scientists at NASA's JPL. So the goal of this was to see how changes, like how ocean changes in like mesoscale affect the atmospheric phenomena. So before deploying this dashboard, scientists would usually ask for like GPU hours and submit some jobs, and the output of that would be a video of, of like multiple fields, but that would not be very interactive. So what we did was we first encoded these datasets into our format, and we deployed them as a web-based service. Now what it did was like scientists could select the field of their interest. They could play everything over time, and they were actually developing like new hypotheses based on like dashboards like this. And so this is a very quick assessment of how the data quality varies. So at the very top left, we have like 100% of the data. But as I said earlier, we provide the ability to query the data at any resolution you want. Like for example, the one at the very bottom right is like less than 1% of the data set. And we tested our workflow with we tested our framework with some workflows that were currently being developed at like NASA JPL, where we plotted the temperature trends using like 100% of the data and compared it with lower resolution of the data sets. For example, we see that when we like decrease the data quality to like less than 1%, we can still see that the general trend of the temperature is to remain. So how it helps is like for workflows that requires downloading of the data like multiple times over and over, you don't always have to query for 100% of the data sets. So there would be cases where you just want to see the data very quickly without downloading all the data. So in cases like those, reducing the data that's served can actually help you. So OpenVisuals is an open source Python library that you can use from Jupyter notebooks or dashboards. It is already like analysis ready and cloud optimized. We also help with metadata conservation with netcdf files, TIFF, jar, and SDF5 as well. And we have been working on developing backend frameworks for libraries like Xarray. Now, another benefit of this is that any data that can be loaded into memory can actually convert it to IDX format. So with very simple commands. So based on all these data, we are also hosting the 2026 IEEE SciVis contest, where the theme of the event will be like visualizing the future of climate science, one dataset at a time. We will be mostly focusing on like 3 different datasets. So the NASA ECHO LLC 4320, that is almost 4 petabytes. The Diamond, that is 1.8 petabytes, and the CMIP6, that is 37 terabytes. So the goal is to democratize the data access to everybody that is out there, maybe on like minority serving institutions or so on. If you want to know more about the contest, you can scan the QR code as well, and there is like a cash prize of $1,000. Now, we have developed all these frameworks for the visualization of the data sets, but These large datasets are often like very inaccessible and usually requires like a prior knowledge of the dataset. So climate scientists who are familiar with like one set of dataset may not be able to extract the same information from the other set of datasets. And there is no integrated framework that lets you query or ask for or perform like analysis on multiple datasets. And again, the new datasets are coming every day, so it is very hard to create one single framework that works for every datasets. So our goal here is to leverage the RAG and LLM to integrate them with the RCMS framework that would enable like scientists to query like dynamic range of datasets or like analysis of the downscale datasets in English language instead of writing bunch of codes. So this is a work in progress. We have not fully implemented this, but the plan is to implement this this RAG using the Azure's like OpenAI service, where we would integrate like climate data with from NASA and other platforms. The first step would be to ingest and index the data set that is already there in like planetary computer and make them searchable via like stack metadata catalog. And then we would be using like GPT-4 to link these datasets with LLMs so that climate scientists or users would basically query the dataset using simple languages, as in English, without having to know like a lot of the data itself. So we believe that using this framework with like Azure AI Studio would significantly enhance the usability and reproducibility of these large-scale datasets. Thank you. And again, I would like to thank all our collaborators with NSDF, NASA, AIMS, JPL, and all these cloud storage providers. Thank you. I would like to take any questions at this point.
So on the last slide, not the acknowledgements, step one is to convert climate data into embeddings. Have you figured out how you're going to do that? What kind of chunking strategy you'll do? And is there any type of standard there?
So we already have like CMIP6 dataset in our own format. Like it's like chunking, but then you are storing the data using this hierarchical layout.
Mm-hmm.
So that allows you to like see the dataset without like having to query the entire dataset. So let's say you just want like a very coarse level of dataset, right? You don't want to know entire thing that's happening. So you can use that. You can use like the Open Business Framework to just say, hey, I need a very coarse resolution of the dataset. So that saves you time, that saves you egress cost because you are not downloading the entire dataset. Mm-hmm. And it's faster as well because the traditional file system, it reads the data from the very top, like as a row measure. Mm-hmm. But instead, we are storing the data as like hierarchy or space filling curves. So it goes like this, mm-hmm.
So in the example of coarser data versus more granular data, do you include metadata that actually the LLM can reference to pull up that this is the coarser section of the initial data set?
Well, so yes, that's a very interesting question. So we already have some parts where we are, setting the latitude, longitude, and like converting them to like the coarser version of the dataset. So we have that in a system as a Python code, but not into LLMs.
Okay, thanks.
Thanks for that talk. That was very impressive, particularly the file format. I was sitting and Googling it. So a lot of the talk at this conference, I think, has been about ZAR, COGS, a lot more standard cloud-native formats. So my question is, did you consider using something like that, and whether the algorithms that are underlying the very amazing compression that you showed could be applied to those formats?
So we would like to think ourselves as a data layout instead of data format.
Okay.
So ZAR, at the very top level, we also support ZAR Open Store. We support NetCDF. We support like libraries like Xarray. So at the very bottom of this is the data layout, like how we are storing the data. So it does not matter if it's ZAR or like, we have tested with ZAR as well. We are compatible with ZAR as well. We actually have like a couple of people reach out to us asking us what's the difference between ZAR and us. And we usually say like we are data layout. Our data layout is like more efficient than Jar as well. So
Interesting. It would be good to chat more. I would like to understand the layout. Thanks.
yeah, thank you.
Isn't this very similar to what our Earth mover is doing with ice chunk?
I have never used ice chunks.
Yeah, because I think they're also trying to solve the same problem, how to have the combined data stores and have the layer above it, organized. So you should talk to Earth mover, they're here.
Oh, yeah, yeah, so the virtualizer is that thing. Okay. Any more questions?
I guess, so since you're at JPL, are there similar efforts across NASA to do this type of work, like retrieval augmented generation?
Actually, this is not a very unique idea. So there are like chatclimate.ai. It's something that's doing the similar stuff for one dataset. So it's not a unique effort, but then this proposal like of working on like large peta-scale of dataset is very unique. But it's not a novel effort. No.